In this video, we're going to conclude our study of gravity. We're going to talk about the general form of gravitational potential energy. We'll also touch on the concept of gravitational fields. Remember, in an earlier video, we discussed the fact that earlier in the course we had used Fg equals mg to figure out the force of gravity on an object near the surface of the Earth. But we now know that more generally, the universal gravitation law allows us to figure out the gravitational force between any two objects a distance r apart. We're going to do the same kind of thing now for gravitational potential energy. So, up to this point in the course, as long as we're near the surface of the Earth, we know that gravitational potential energy is given by the formula U equals mgy. And that, in combination with the work energy principle, allowed us to solve many problems. However, the problem with this formula is if the object, let's say, is up here and not just near the surface of the Earth, it doesn't work. Here is the more general formula for gravitational potential energy. So specifically, if I have an object like the Earth and I've got an object up here, so here's m1 and here's m2, the gravitational potential energy that m2 has, a distance r away, is given by this formula. Now, one of the things that's a little bit confusing about this formula when you first see it is that minus sign. You'll notice that gravitational potential energy with this more general formula is always negative. But I want to just show you that it makes sense. We know that near the surface of the Earth, if I take an object and I move it from here to here, that object gained gravitational potential energy. So in the same way, if I take an object and I move it from, let's say, this position r1 to this position r2, it should also gain gravitational potential energy. Well, you'll notice that the bigger I make r, the smaller this value gets, and therefore the gravitational potential energy at r2 is less negative than at r1. In other words, the gravitational potential energy here is greater than here. So it works correctly. Remember also that ultimately what the potential energy is at any point isn't really important. It's how the potential energy changes. We see that in the work energy principle, that U doesn't show up. What shows up is delta U. And so the key thing is always changes in potential energy are the only thing that's significant. Because remember, even in this case up here, we can set the origin. If we set the origin to be 0 right here, then this object would have negative potential energy. Doesn't matter, doesn't change what delta U would be. You'll notice, by the way, when I wrote the work energy principle here, I assumed that the work done by non-conservative forces is equal to 0. That's simply because we're going to look at the situation where there's no friction and no applied forces. So let's see how we can use this new formula to solve a problem. A rocket is launched with an initial velocity of 2.5 times 10 to the third meters per second. What is the greatest distance it will reach from the center of the Earth? First of all, just a couple things to understand about this problem. The first is that we're assuming that there's no atmosphere. We're not worried about air resistance. The other thing is when we say launched, we really mean like it's thrown. In other words, we're not talking about a rocket that is continuously firing its engines. We're assuming basically that it's like throwing a ball up, so that the initial velocity v0 is equal to 2.5 times 10 to the third meters per second, and there is no additional force being exerted on the rocket other than just the force of gravity. You'll notice then that our rocket starts out at an initial distance from the Earth of the radius of the Earth. Remember that for gravitation, whether we're talking about gravitational potential energy or the gravitational force, it's the distance between the centers of the objects that matter. So that's our initial position, and we're trying to figure out how high up this object will get. And so r is what we're trying to find. Notice too that we're assuming that at the highest point, that's where the velocity would be 0, just like taking a ball and throwing it up from your hand. The farthest it gets from your hand is when the velocity is equal to 0. Okay, so let's see how we would solve this problem. Just like any conservation of energy problem, the first thing we want to write down is the work energy principle. And again, here we're going to go right to the form where it equals 0 because there is no work being done by non-conservative forces. The next thing we want to do, again, is just what we would have done when we covered conservation of energy earlier. We're just going to write down what delta K and delta U are. I've got 1/2 mv squared minus 1/2 mv naught squared. So there's our change in kinetic energy. And then I also have the change in gravitational potential energy. Now here I've got to just be careful because there's a minus sign in the formula. So normally it would be plus final minus initial, right? That's what delta U would mean. But here it's going to be minus final plus initial. And so our final r is what we're trying to find, and then plus g mass of the Earth, mass of the spaceship, divided by the initial distance between the two, which again is r naught. And in fact, let me go ahead and just write that as re. Okay, and that's got to equal 0. So again, because the formula has the minus sign in here, delta U is going to be minus plus instead of the usual plus minus. That's one thing to watch out for. Okay, now we just want to solve for r. And you'll notice that right away we can cancel out the mass of the spaceship. So we get rid of all the m's. The mass of the Earth, however, does not cancel out. Then let's look at if any of these four terms are 0. Well, notice that since the final velocity is 0, there is no final kinetic energy. And so that whole term is going to go away. Let me rearrange this equation a little bit. Let me start to get it in the form where we can solve for r. And again, I want to do this algebraically as always. So I'm going to bring this term to the other side, but then I'm going to reverse the way I write them. So I get g mass of the Earth over r is equal to g mass of the Earth over the radius of the Earth minus v naught squared over 2. So let me go ahead and copy that to the next slide. So we had g mass of the Earth over r is equal to g mass of the Earth over the radius of the Earth minus v naught squared over 2. Now I need to solve that for r. The way I think about this is I think of all of this as one unit. I'm trying to solve for r, so basically I want to just cross multiply. In other words, if r comes up into the numerator, then this whole thing has to go down into the denominator. And therefore what I end up with is GME over that entire thing, GME over RE minus V naught squared over 2. And that is my algebraic solution for how high the rocket gets. I'll leave it to you to check my math. What I got when I solved the problem was I got r is equal to 6.7 times 10 to the 6th meters. Make sure that you do go through and work out that calculation, because this kind of formula you want to be really comfortable solving with your calculator. It takes practice. So just go ahead, plug in the numbers, and make sure you agree with my answer. Let's look at another common problem that's done in most physics courses. And this involves the concept of escape velocity. So I want you to think about the idea of throwing a ball up in the air. I throw it up, it goes up a certain height, comes back down. If I throw it up faster with an initial higher velocity, we know it goes up higher. Is there a velocity that you can throw the object up with so that it never comes back down? That's the question, and the answer is there is, and we call that the escape velocity. So what is the minimum velocity I have to throw something up with so it literally never comes back down? Well, let's think about what the picture looks like. It's pretty similar to our last problem. The first thing is that our initial position of our rocket is once again just equal to the radius of the Earth. So that's where it starts out. Now what we don't know is the initial velocity. That's what we're trying to find. What initial velocity do I have to give this object so it literally never comes back down? So where does the object end up then? Well, if I'm looking for the minimum velocity for it to never come back down, basically what I'm saying is when the rocket gets to infinity, its velocity is equal to 0. So that's the condition to find the escape velocity. Now, if I give it a greater initial velocity than the escape velocity, it simply would be moving even as it gets towards infinity. Okay, so once again, it's a conservation of energy problem. We know our first step is to write delta K plus delta U is equal to 0. Again, we're ignoring air resistance, no other applied forces acting. Next step, same thing, write out what these represent. Delta K represents 1/2 mv squared minus 1/2 mv naught squared. Delta U, remember, is final minus initial, but it's negative g mass of the Earth, mass of the object, divided by the final separation between the two, and then plus g me m. And this would be over r naught. And once again, I'm going to just right away put in that that's the radius of the Earth. And that has to equal 0. Okay, let's see what we can get rid of here. First of all, once again, you'll notice the mass of the object goes away. So those all go away. But now let's look at if any of the big terms go away. You'll notice that definitely the final kinetic energy goes away because we're solving for the object no longer moving when it gets infinitely far away. The other term, though, that goes away is this one, because if r approaches infinity, that term definitely approaches 0. And so this is actually an easier problem than the one we did before because we're only left with two terms. We've got v naught squared over 2 is equal to g me over re. And therefore, the escape velocity can be found by simply taking the square root of 2g mass of the Earth over re. So let's go ahead and just plug those numbers in. V naught is equal to the square root of 2 times 6.67 times 10 to the negative 11th times the mass of the Earth, which is 5.97 times 10 to the 24th, dividing that by the radius of the Earth, which is 6.37 times 10 to the 6th. And if you work that out, and again, I encourage you to just always do these on your own, check them, make sure you agree with me, I got that V naught was 1.1 times 10 to the 4th meters per second. So that would be the escape velocity of Earth. Now, obviously, because Earth has an atmosphere, you couldn't just shoot something with an initial velocity of this and actually have it get away. Now, if you're on the surface of the moon, then this kind of calculation makes has more validity because literally there's no atmosphere on the moon. The last thing that I want to talk about in our study of gravity is the concept of gravitational fields. And this is really just to get you to start thinking about the concept of a field, which you'll need in your next course when you start looking at electric and magnetic fields. Think about most forces that you experience in your everyday lives. Most forces are what we call contact forces. And that means, if you want to exert a force on your coffee cup, you have to make contact with it. It's not that you can hold your hand some distance away from your coffee cup and have something happen, right? We're not magicians. We can't make things move without touching them. So most of the forces we're familiar with are contact forces. However, we all know that there are some key examples of forces that aren't contact forces. Think of the force of gravity. If you take your pencil and you just let it go, somehow the Earth can exert a force on that pencil without touching the pencil. You're probably familiar, I'm sure you played with magnets at some point in your life, and you know if you move one magnet near another magnet, again, that second magnet will move. You didn't need contact. So the gravitational force and the electromagnetic force, which encompasses both electricity and magnetism, those forces act over a distance. And we call those action at a distance forces. So here's the question. How quickly would the Earth react if something happened to the Sun? You'll notice that with these action at a distance forces, if something is very far away, is there some time delay? Well, let's look at this. So here's the Sun, and way over here is the Earth, orbiting around the Sun. Well, what happens if we've got a sun-eating monster? Here's our sun-eating monster. And what would happen if our sun-eating monster all of a sudden came up, ate the sun, and went away? So all of a sudden, the sun disappears. Well, what would the Earth do? We know that if the sun isn't there to exert a force on the Earth wants to obey Newton's first law and go off in a straight line. So here's the question. How quickly would that happen? Would it happen instantaneously, or would there be some delay? You'll notice that Newton's law of universal gravitation, G m1 m2 over r squared, doesn't help us out to figure this out because there's no time in the equation. Well, it turns out that we know the answer now. It would take 8 minutes. So if the sun somehow magically disappeared and was no longer there in space, it would be 8 minutes before the Earth would go off in a straight line. 8 minutes is actually the amount of time it takes for light to travel from the sun to the Earth. So it turns out that the speed of light is also the speed at which gravity works. So why that is a way more advanced topic, but I want to kind of introduce the idea to you here that basically as soon as we couldn't see the sun anymore, because that's the 8 minutes it would have taken for the light to get to us, that's when the planet would go off in a straight line. Think about this right now. When you look up and see the sun, you're not seeing it how it is at this moment. You're seeing it how it was 8 minutes ago. And that's, of course, always true. So what we do in physics nowadays is we look at this in a little bit different way. And again, I'm just introducing the idea to you here, but we're going to develop this much more when we talk about electricity and magnetism in the next course. We introduce the concept of a field. We say a gravitational field surrounds every object that has mass, and this field permeates all of space. A second object near the first object experiences a force due to the gravitational field. Now, at first this might not seem like any big change to you, but effectively we've inserted a middleman or middlewoman in the situation. In other words, instead of thinking the Earth directly exerts a force on the moon, or that the sun directly exerts a force on the Earth, what we think of is that the Earth creates a gravitational field, and that's going off in all directions. And the reason that the moon experiences a force is not directly because of the Earth, but because of the gravitational field that it's in that was created by the Earth. Now, how does this solve our problem of this time delay? Well, now what we can imagine is that if something happens to the Earth, it takes a while for that change to propagate through the gravitational field. The best analogy of this, I think, is thinking about what happens on a lake. So here we have a lake, And let's say over here we've got a cork floating in the lake. What happens if I drop a rock into the lake over here? Does the cork immediately start moving? The answer is, of course, no. The waves have to propagate to the cork. And then once those waves get to the cork now knows that there was a disturbance that happened over here. That's exactly what happens with a gravitational field. If somehow, I don't know, we've got another monster, comes up and kicks the Earth, how would the moon know about it? Well, it wouldn't know about it instantly. That change in the Earth's position would have to propagate through the gravitational field, and that's when the Earth would find out about it. Okay. By the way, if you've paid attention at all to important advances in physics over the last few years, you may have heard of the concept of gravitational waves. This is exactly what they're talking about. And in our next course, once we talk more about the concept of gravitational or electric and magnetic fields, I'll actually talk about that with you. Okay, so what do I want you to take away from this? I want you to take away that our modern way of looking at these gravitational interactions, like the Earth exerting a force on the moon, is instead of thinking of the Earth directly exerting a force on the moon, we think that the way we think of it is the Earth creates a gravitational field, and then the moon experiences a force because it's in that gravitational field. Okay? So for example, why do you experience a force of gravity? The Earth is creating a gravitational field. You are a mass in that gravitational field, so you experience a force. Okay, that's going to end our study of gravity.